Welcome to this week's Aspen Colloquium. This week it will be presenting the microscopic origin of black hole entropy workshop. And it will be given by Clifford Johnson. Clifford got his PhD in Southampton, then was a postdoc at Princeton and Santa Barbara, then a faculty at Kentucky and Durham, USC, and now he's at UCSB. And since I'm going to be a strict timekeeper for 50 minutes to leave us 10 minutes for questions, I will turn the floor over to Clifford, who will tell us about how Wigner meets Hooft near the black hole horizon. All right.
Thank you. So it's a pleasure to be here. Thanks to everyone for coming, and also thank you for the invitation, the colloquium organizers. So I'm going to try and tell you a little bit of a story which interweaves a number of themes that exciting in various areas of physics come together very nicely in the context of understanding black holes. There's some sort of cartoon drawings of them I made, and what I'll try and do at the various points is mention some of the things that are actually going on in the workshop, if I can, and some of the launch points, and hopefully get you excited, and you can ask participants in the workshop for more details as you see fit. So one of the things that you probably know is that we're very excited as a physics community quite broadly, whatever field you're from, the fact that we are being able to make measurements on black holes is very exciting. There's been surprises coming in from the fact that these black hole collisions that are being observed using gravitational wave observatories. This is probably an already out-of-date poster from LIGO, Ergo, Kagura, telling us that there's a wide range of black holes in the astrophysics world. As we know, they come out on paper at any size, and you may wonder, well, maybe they only get made as large astrophysical objects. But there are more and more reasons to believe that, both theoretical and perhaps otherwise, that there's a range of scales over which we need to understand black holes. There's another scale, the supermassive ones. And we should also be looking in the other direction. And in the other direction, where they're much smaller, we really need to take seriously the quantum effects. And the fact is that we don't have a theory of quantum gravity, which is what you really need to understand this. Well, we have some theories of quantum gravity, but getting them to really tell us things about black holes is still very hard. I'd like to tell you about some of the themes that have been coming up, some of the progress that's been made in recent times, and see if we can cheer ourselves up that there's some progress going on. So one of the questions might be, well, what is quantum gravity? What should it be? We don't really have experimental clues. So knowing exactly what that looks like is still a bit of a guess. So the best, most straightforward guess is to mimic what we've seen in other areas of quantum theory. And of course, we have the path integral formulation of quantum mechanics and more generally quantum field theory, which tells us we should sum over all the dynamics with some weight given by the action and see whether that can actually work. And of course, it works extremely well in particle physics. Maybe it might work here. So that's one thing we might try and do. And what we're hoping to do is find a formulation that will allow us to address black holes fully as quantum mechanical objects, but it's also relevant for understanding the very early universe, where again we're driven to understand the quantum physics of gravity. And of course, there are clues that something different must happen. There are clues as to what quantum gravity must do. The first pass, the cartoon you may be all familiar with, is the fact that on the one hand, we have the general relativity, which gives us things like horizons, one-way doors. And on the other hand, we have quantum field theory, quantum physics that tells us that the vacuum is seething with possibility. We have pair creation. and we can borrow from the vacuum for a short amount of time, given the mass of the particles and antiparticles, and that's just fine. We can compute that. We know that's a thing. These two things don't play well with each other. Of course, the thing that gives is general relativity. And you have the cartoon that actually, if that pair creation happens near a horizon, one of those virtual particles can fall in, then it can't emerge. And so its partner is no longer a virtual particle. It's a real particle that can fly off to infinity. Then we see that as radiation. So this is a cartoon of one way of thinking about the origin of Hawking radiation, telling us that quantum mechanically, black hole is actually radiating. And I neglected today to put in all the units, but if you did, you would see this is control that temperature. There's an H bar on the top line telling us about this being a quantum effect. Of course, in those massive astrophysical black holes, that's such a negligible effect. We don't worry about it, but it's telling us something deep about what we should understand about how black holes work. And moreover, if you continue the calculation, it implies also that black holes have an entropy, and they're beginning to behave like they behave, at least first pass in this semi-classical approach, as thermodynamic objects. And I'll say a little bit more about that in a moment. This is the famous Bekenstein-Hawking entropy formula on the right, and given the Hawking temperature. So I've just done this for a simple, the Schwarzschild black hole just has the one parameter, the mass, and I'll say a little bit more later. Now let's try and do a little bit better than this. Let's do a second pass at what we might expect from quantum gravity. Let's do what I said a few slides ago. Let's attempt to mimic what we learned. Let me see if this actually works. You see that? Yes, it does work. Let's try and make sense of this picture where we're doing dynamical paths and extend that to gravity. It would suggest that we should sum over the dynamical object in gravity, which is geometry itself. So I should sum over all possible geometries for a given space-time with perhaps some asymptotic constraints. I'll tell you about it in a moment. I need to make sense of how to do that sum, how to make that path integral make sense. And well, space-time can change topology as well. So why don't we also see whether that's something we should do as well? So let's try and sum over topologies as well, see if we can do that in some sensible way. This motivates a thing called the gravitational path integral, which sometimes I will call just GPI. And so it's sum, here's the partition function, it's sum integral over geometries, possibly phi standing for some matter content that lives in that geometry. There's the action, which might be, say, the Einstein-Hilbert action equal to matter in some way. And so perhaps I should be doing something like that. Well, if you follow your nose, it turns out in the usual way where we try and understand how to do very hard integrals, we look for saddles. The things that satisfy the equations of motion then turn out to be important. They turn out to dominate the action, construction. And so if we take, for example, solution I mentioned before, which is just the single parameter black hole, just has the mass of the Schwarzschild solution you learned about in general relativity class. We can study that as a saddle of the gravitational path integral and try and understand its properties in that sense. And one of the things that we might do, in fact, it helps make sense of the saddle, is to go to Euclidean time. And from other perspectives we know in physics, that's actually quite useful because that's also telling us about the quantum system at some finite temperature, where I work with some Euclidean time, which has some period which sets the temperature, the period beta, 1 over temperature. So you can actually do that, but now you do that in the actual geometry of the solution by construction in the as a saddle of the path integral. Now, when you do that, well, let's look at the coordinates. We're in 4 dimensions. We surround the black hole with angular coordinates theta and phi, and then we have a radial coordinate and some time. I've now made time Euclidean, as I said, with some period. If I look at the RT plane, that's time going around, and then radially it's R. That actually, for arbitrary period, gives you a solution that is singular. It has a conical singularity. The period of beta cannot be arbitrary, So to have a nice smooth solution, which is what we started with, we should actually fix beta to make sure that the conical singularity goes away at the origin. The origin turns out to be where the horizon of the solution is. When you do that, it puts a condition on beta, and that turns out to be Hawking temperature. So this is a different way of computing the Hawking temperature. Instead of doing quantum field theory in some background space-time, you can do this easier calculation where you simply look the properties of saddles in your path integral calculation. That actually then allows you to treat that partition function in the way you would in an ordinary quantum mechanical, even classical thermodynamic system. Now there's some action you can derive, you can take derivatives and compute things. That's the natural way of getting, for example, the entropy that I talked about earlier. So the temperature for the black hole, the Schwarzschild black hole, look like that. There's a formula you can derive for, say, a black hole, the Rising-Norton black hole with some charge. You can do it for rotating black holes with some spin J. Difference between the Schwarzschild case and these cases, for example, is that you have a nice situation where the mass reaches a special value and makes the temperature go to 0. We're actually going to focus on that shortly. And that's the case that's called Extremal. Those turn out to be the ones where we have best control in the story so far. So I'm not here to talk a lot about the whole story of black hole thermodynamics, etc., except to say that those are the first steps to studying in semi-classical gravity what the black hole thermodynamics looks like. It was long noticed before any of this quantum stuff that doing operations on black holes, the area to which the entropy is proportional, the area seems naturally non-decreasing. That was already suggested by Bekenstein to be an analog of the second law, and it really comes to fruition then in this full quantum setting, or semi-classical quantum setting. You can write an analog of the first law, and so on and so forth. But the full if you take this seriously, the black hole's entropy has consequences. It's telling us that there should be some underlying microscopic description. There should be quantum microstates that we should be able to describe and get to grips with. There should be some finite dimensional Hilbert space given roughly by the Boltzmann count of the number of states. So how can we explore that in a full theory of quantum gravity? How do we even begin to formulate that? So that's one of the things people are trying to understand. And there's a lot of trying to understand at this workshop, entropy in its various guises, and how to make sense of that. Even in the semi-classical approximation where we have good control, there's still a lot to be understood. So recall then, we had this set up where we want to sum over everything that the geometry can do. And so the question is, can we? Do we have any good models of this? And the answer is yes. I'm going to tell you a little bit more about that. So let's dig a little bit more deeply into the charged black hole example. Let's do a calculation together. So this is the Rising-Norton black hole that, again, if you haven't thought about it for a while, you probably saw maybe in a general relativity class or something. And the idea is that it now has two parameters, the mass and the charge. And the horizon, I remind you, is where this piece, well, for this class of solutions, where this piece vanishes. And that is, let's see, okay. And then the extremal solution is also where the mass is equal to the charge. As I said before, I have t equals 0. What I'm going to do is I'm actually going to change to a coordinate where I actually use capital R instead of little r. It gets written in this nice form like this. And there's some nice features of this. If I look, for example, at r goes to infinity, far away, this is just the line element for flat space, telling me I'm far away from the black hole. And the horizon is at r equals 0 in this coordinate. So I have two interesting pieces. I have the faraway bit where I have large r, and I have the small bit, which is the horizon. And in that limit, horizon actually takes an interesting form. geometry breaks down from being a piece that is a structure that's entirely four-dimensional as up here, where I have four coordinates mixing up nicely. I have instead a factor geometry where I have a two-dimensional piece and another two-dimensional piece. And so the picture of that looks like this. And far away is sort of where this sort of flattens out. Then as I go toward the what's called the throat region, the geometry changes its character. There's a constant radius S2, which I've represented as a circle. Then there's the radial coordinate in time, which actually form the ADS2 geometry, and I'll remind you what that is shortly. So this is the extremal limit of the geometry. And here are the two players that I mentioned before. So I have the radial coordinate and I have the time, which is a circle. And that actually has this hyperbolic form to it, which is very, very familiar from posters we all probably had on our walls when we were undergraduates. Key feature of this kind of geometry with this metric is that lengths diverge at the boundary as you move, and you can see that. How many fish can I fit into a given fixed thing? And what that actually means is that that period that we talked about, which is how much I go around in a circle here, as I go out to the boundary, goes to infinity. And that fits because we're doing this extremal t equals 0 geometry. And then I'm sometimes going to represent this hyperbolic geometry as a little sort of bit shape like that, just because it takes up less room and reminds you that it's hyperbolic. Okay. But what I want to do is actually not just the extremal case, but to talk about some of the dynamics. We'll turn on some dynamics. So I want to actually have some temperature. We can do some of the thermodynamics. And that leads to, this was some of the recent work now, starting in the sort of 2010s. I'm going to put lots of people in these dots. It's the idea that instead you're looking at just a piece of the geometry. If you actually look at the near horizon geometry at low but not zero temperature, you'll instead get a piece of ADS2. And so the picture I'm going to draw is that you have a boundary. Think of it as a circle initially. That's not all the way out to infinity. So then that would be at finite temperatures. Length hasn't diverged. That'll tell me about finite temperature. Then I'm also going to have an additional degree of freedom, which corresponds to the fact that I have, for example, that S2 that got fixed geometry as I went all the way to t equals 0, that can actually fluctuate its size a little bit. And so there's a scalar in the reduced two-dimensional model that actually keeps track of those dynamics. You end up with a little model of two-dimensional gravity that captures the near horizon geometry of this high-dimensional black hole, which at low temperature, which is called a JT gravity. It's the Joukiffe-Teitelbaum gravity. It was found for just as exploration of low-dimensional gravities separately by these two authors a long time ago, then was recognized as relevant to precisely the questions we're interested in later. The way to read this is that I have so R here is the Ricci scalar. I have a linear coupling of the scalar phi. So its equations of motion tell me that it should act as a Lagrange multiplier, simply fixing that to 0. That tells me that I should have constant negative curvature geometry, and that is precisely what ADS2 is locally. There's the usual Einstein-Hilbert term that you would have in gravity, but in 2 dimensions, that just counts topology of the surface. There's no dynamics there. What happens is that there's a number, there's a scalar, not a scalar, there's a number, what I'm going to call S0, which turns out to be the entropy of the black hole at t equals 0. So that's going to be a reference number that tells us about that black hole. That's typically going to be large for we're doing a semi-classical analysis. We want black hole curvatures to be nicely well behaved. We have large black holes. This is some number that'll go there. And then there's a boundary term, which involves essentially a boundary version of this piece. And what actually happens quite nicely is that the equations of motion in the bulk just force the curvature condition. Then all the dynamics end up just on the boundary. And when you look at the boundary, which essentially is this bit where I go out to, not all the way to infinity, the dynamics on that boundary, when you look more carefully, is an action, which is called the Schwarzschild action. And all of the physics then turns out to be allowing this to have some fixed length beta, telling me what the inverse temperature is, but it can then fluctuate according to the dynamics that we get from this term, the Schwarzschild dynamics. So that's a field theory problem of great interest. You can go ahead and solve. You can solve at leading order in a sense I'll talk about in a moment. And it's some function of beta that turns out to be this. That's the partition function. I can do a Laplace transform of that to try and understand the density of states in this model. And if I do that Laplace transform, I get the following function. So it looks like sinh of root E divided by, with some numbers. So there's a very important piece here I'm going to tell you about on the next slide, but I put it here. I'm going to cheekily call this H bar. This isn't the H bar that is of the quantum mechanics. It's just a name. So what it is E to the minus S naught. Remember I said S naught is large for a black hole where we have control over semi-classical physics. So that's a small parameter. And it's going to be an expansion parameter in a moment. Okay, so let me just say a little bit more about that. Because that S naught multiplies the topological term in the action is exponentiated, then we can actually keep track of topology of the space-time. We wish to sum over that, which is what we're going to try and do as well. So the leading piece came with an E to the S naught, which I've written as H bar to the minus 1. And as I increase the topology by adding, as I change the topology by adding handles for some fixed temperature length of that boundary, I get additional powers of H bar, which go according to minus the Euler number. So that's a nice expansion parameter. It's actually an asymptotic series that we can try and understand. But the leading piece has this nice sinh root E behavior, which starts at 0 and grows exponentially at large E. So this is supposedly something about the density of states of this black hole in this situation. We're going to need to try and understand how to do this. So here's a landmark result. All of those diagrams I mentioned, order by order in perturbation theory, can be computed. The path integral can be done partly because it's such a relatively simple theory. There's very little in the way of bulk dynamics. It's really topology and then those boundary dynamics and gluing things together in the right way, which I don't have time to explain, and tell you how to do the path integral and how to do the sum over geometry and topology for this particular exactly solvable model. And that is one of the landmark results of Saad, Schenker, and Stanford. It would have been really cool as a result if that's all they did in the paper, but of course they did more. Because they also showed that there's a completely separate way of computing those same diagrams. That is that it's equivalent to doing a computation order by order in a random matrix model, where you have a large N random matrix model. And as you probably know, due to Hooft, I'll explain in a moment, there's a 1 over N expansion taking into account topology there. And the 1 over N should then be identified in some sense that E to the minus S naught of the black hole. For the dictionary, the details shouldn't concern you too much, but the dictionary looks something like this. I have on the one hand, let's look at the random matrix model. It looks something like this. As as particle theorists, we tend to pretend that it's a toy field theory. Really, it's a probability problem. I'm asking that I draw an n by n emission matrix model with some probability given by e to the minus trace some polynomial of m. That's a number. I can compute that probability. And the partition function I've written here is the normalizer. I sum over all possibilities in the usual way. But one way of thinking about this is it looks a little bit like a field theory. And I can do what Hooft tells me, which is that I have a matrix valued field. This gives me kinetic terms. The polynomial terms gives me vertices. I can work out Feynman rules. And I draw Feynman rules, which turn out to be these double line diagrams, which you can think of as the two lines are propagating the separate indices of the matrices in some consistent way. But I can draw dual diagrams to this. I decorate in the way given in the figure. It looks like I'm tessellating some surface with polygons. Every diagram that I draw can be thought of as a tessellation of some diagram of some surface. There's an organization in terms of topology I'll explain on the next slide. And the business of summing over all possible diagrams is then the business of summing over all possible tessellations. That's a really great way of doing what we wanted, which is to enumerate geometry in some controlled way. If we could take a continuum limit, and there's a way of doing that, I'll mention that in a moment, we can actually do the path integral in this case. You can see this is very well adapted to two-dimensional discussion. It would be great if progress could be made in higher dimensions, but doing two-dimensional gravity here, so maybe it has a chance of working. So anyway, there's some comments here about some links to beautiful mathematics that AAAS used to really motivate, even without knowing explicitly what the matrix model potential was. There's certain recursion techniques due to Mirzakhani and Eynard and Orentin in the context of matrix models that can tell you how to, knowing the leading order spectral density that I computed before, deduce all the higher order terms recursively. So they're able to show that there's a one-to-one correspondence between that and all the diagrams you want to draw in perturbation theory, topological perturbation theory. Okay, so let me say a little bit more about matrix models. The trace, and oh, no, sorry, I'll say that on the next slide. I was just going to expand a little bit more on the Hooftian thing of drawing the diagrams. You can actually, in this case of just the quartic, you can actually just do it while I babble here. You can actually compute your Feynman diagrams, compute your Feynman rules, taking into account the n out here, which I didn't have on the previous slide, and see that diagram like this, for example, which I can draw without disturbing the ordering of the ribbon and breaking it in some way. I can draw that on a plane or the surface of a sphere, is different from this one, which is an allowed diagram, which I could not draw on the surface of the sphere, but I can draw on a torus without having these things overlap each other. If you count the powers of n, you'll find that the torus is down by a factor of n squared compared to the plane, the sphere. And if I had a double torus, you'd see there'd be an extra n squared. And it's doing exactly what we outlined on the previous slide. So large n captures topology. Then the continuum limit turns out to be finding a critical point in coupling space. I didn't tell you what that coupling was because I wanted to have it arbitrary until I tuned to a critical point where the diagrams with lots of the tessellating triangles or whatever I've chosen, pentagons, what have you, those actually turn out to dominate over diagrams with only a few in such a way that I am getting better and better approximations to the surfaces. I can make a surface smoother and smoother for a given fixed area back in more and more and more triangles. So there's a way of finding universal physics that sort of forgets about whether I chose triangles or squares or what have you. Certain details of the potential go away, and there's universal physics to be found. This is an old technique which goes back to the 90s, which is called the double scaling limit in this context. So what people often do is diagonalize the matrix models to solve using the fact that I have a UN invariance because I have a trace on in my action, and it allows you to work instead with the eigenvalues, which at the end of our procedure will be the energy states of the black hole, and this will be a guide to the sort of leading behavior. And I want to tell you what the double scaling limit looks like in this language. In this language, what happens, I get a Jacobian from doing this, very famously known as the van der Waals determinant. It's like this. It's like a repulsion term. If I exponentiated this, it would look like a log of the difference of eigenvalues telling you that you don't want them to get too close to each other. We're going to come back to that later. So this is a very important feature of random matrix spectra. This is often referred to as a Dyson gas, where it looks like a one-dimensional problem with particles with positions labeled by lambda I, n of them, and they're in some attractive potential given by the potential we wrote down. Then there's some repulsive piece, particles pushing each other out, and if you solve that problem, you find that at leading order at large n, you have a solution, a stationary saddle point solution, which is a sort of droplet. Double scaling limit turns out then to be place, which you remember is where you find a continuum limit that has universal physics. Turns out to be the business of zooming into one or other of the endpoints of this model, of this density. And so if I relabel my near endpoint coordinate as E, picture I told you about with regard to gravity turns out to be for some potential, which we don't know explicitly, which is way more complicated than this, but implicitly, this spectral density that's relevant to the gravity problem should be thought of as the endpoint of some double scaling limit process of some complicated matrix model potential, at least order by order in perturbation theory. Okay. There's got to be more, as we'll see in a moment. I have that counting expansion parameter that I told you before, counting topology, and it's an asymptotic expansion. I can't just resum that and have the whole answer. There's stuff that's beyond perturbation theory, and that's going to be hugely important. That's been particularly the subject of my research. So one of the things, these matrix models have been used for many years in other contexts, in the context of trying to understand how to build models of string theories back in the 90s when the double scaling limit first appeared. And even back then, this whole business of what happens beyond perturbation theory, this perturbative series, it was still, not, language was only partially developed. There's some non-perturbative effects we could understand, but having a nice picture of what the non-perturbative effects really mean and how you can compute them was still being developed back then. What actually happened, interestingly, is that there were two communities. There were the physics people interested in random matrix models, the string theory people interested in random matrix models who were led to it by that Hooftian picture I told you about. There's also stat-mech type physicists who are interested in random matrix models because of lots of reasons, and some to do with enumerating surfaces, some not, some to do with being nice examples of stat-mech problems that you can study, and so on and so forth. Some motivated by Wigner's original task for bringing them into physics. I'll say a bit about that later. Very interestingly, the physics community on the gravity side were interested in it from a string theory perspective back in the early 90s, got interested in other things after a while and went off, and lots of exciting things happened. Other random matrix model communities continued studying random matrix models and developed all sorts of beautiful non-perturbative techniques, which carried on some of the non-perturbative techniques that the string theory people had developed. But most of our community never looked back, which is sort of interesting. And so it's only in recent times, I think, we've been reconnecting with some of those lovely developments. And I'll say a little bit about that in a moment. This all might be a little bit abstract, this random matrix model. So I'm actually going to ask you to just try something yourself. I'm babbling a lot. So you can just get out your phone and code this up. It's a few lines of code. You can actually just do what I said, right? Code up a few lines of code to generate a matrix model with Gaussian probability. This is the classic random matrix model problem. And then every time you pick one of these matrices, compute the eigenvalues and histogram them. Okay, and off you go. And you'll verify a number of things you learned about in, baby's first random matrix model class, if you took that one, right? Which is that you should get the Wigner semicircle law and so forth. With a bit of scaling, you can get this to come out quite nicely. Scale things in such that the endpoints don't flow with n. So you use scaled eigenvalues. And so if you were to do that, you would get the Wigner semicircle law, which in this case we can solve exactly. And the zooming in, the double scaling limit, the analog of that here, although there isn't a coupling of this form I told you about before, there's a placeholder for it, is that zooming into the endpoint, and you'll get this root E behavior. You'll get something I call 1 over n with some scaling parameter, which goes to 0 as n goes to infinity. And there's some finite thing I can hold fixed, which is some renormalized value of the 1 over n, which I'm going to call h bar. And it'll resonate with the e to the minus s naught I told you about later. It'll be the topological expansion parameter in the double scaling limit. Now, it turns out this model is exactly solvable in this edge endpoint, right? Just to be clear, this... You zoom in here, and I get all of this behavior. And you'll see that I get a lot of structure when I zoom in. Okay? I don't just get the root E behavior, which I get by scaling the leading order piece, which is the Wigner semicircle. There's a bunch of wiggles, and in fact, there's an exponentially small tail that goes off to infinity that way, and there's a lot of structure. That's all the non-perturbative physics. We'd like to capture the analog of that in our gravity problem. In case you're wondering why this doesn't quite match, it's because I'm using 100 by 100 matrices as opposed to infinite by infinite ones. And the exact result you can compute mathematically is seeing that. The non-perturbative formulation of these random matrix models, which I'll briefly mention, this goes way back to the 70s, where you write things in terms of a family of orthogonal polynomials, which are orthogonal with respect to the measure of the random matrix model itself. And they satisfy certain recursion relations. Again, if this is looking very abstract, in the Gaussian case, these orthogonal polynomials are just the Hermite polynomials, which you know and love from quantum mechanics, the harmonic oscillator. But for arbitrary potential, there's a more interesting family. And so for our gravity problem, there exists orthogonal polynomials which you could find if you so desired. And there are no approximations here. You can compute everything. Principle, if you could find the orthogonal polynomials, you could find everything about the model. So I'll say a couple of things. There's the orthogonal polynomials, in terms of which you can write and ask any question in the random matrix model equivalently in terms of their properties. They have a recursion parameter I'm going to call R. In the large N double scaling limit, this thing becomes a function, which I'm going to call U of X. And the index X is simply, the index on a polynomial simply is going to become a continuous coordinate that I'm going to call X. And so that defines that there. And then there's the usual, I've got to some endpoint plus a little bit E, and that defines E in the way I had previously. Okay, so at the end of the day, finding non-perturbative physics turns out to be rather interesting. And auxiliary quantum mechanics emerges in this formalism. It tells me in the large n double scaling limit, these orthogonal polynomials turn out to be wave functions, some Hamiltonian problem, one-dimensional Hamiltonian problem with some potential. But the business of finding the orthogonal polynomials turns out to be solving the wave functions of this problem. And in general, this u of x function here ultimately defines the whole problem, will be defined by some nonlinear ODE. And one way of solving the whole problem, the business of solving the whole problem and defining it non-perturbatively, is really finding and solving that nonlinear ODE. I won't say anything more about that, except it can be done. And in the case I just showed you the exact solution for, these wave functions are actually Airy functions. And you could see that that exact solution of those wiggles I wrote down for you before actually are Airy function, is built out of Airy functions. There's a generalization of this for very complicated problems, which a lot of my work in trying to define things non-perturbatively to build on, to go beyond what AAAS did, was to try and write matrix models in this language, which allows you access to non-perturbative physics. So the answer is yes, you can do this for JT gravity. And by JT here, to avoid some subtleties with the vanilla JT, I'm just going to say, I mean, JT, there's some supersymmetric versions of this called JT supergravity. There's deformations of it and so forth. What I'm about to say can be done for that larger class, but I'll just continue calling it JT gravity simplicity. But even if it can, we still might want to know what does beyond perturbation theory mean? What does that mean physically? So anyway, so some of this is another title could have been what I did during the pandemic. But anyway. So yes, you can find the appropriate problem, this auxiliary Hamiltonian problem. You can find the equation for this, you can solve it. It's highly nonlinear, so at this point. You put it on a computer and solve it numerically, find the wave functions numerically, build, and here are some of the results. So that line I gave you before, that was the Schwartzian. Then we have AAAS showed that order by order in perturbation theory, it's a random matrix model. Now, non-perturbatively, you can compute the analog of those wiggles that we saw in that toy model of the Gaussian case. Okay, but you should be concerned. Right, how is our quantum gravity a probabilistic ensemble? Where did that come from? Right, we're doing this path integral. And also, worse than that, where does this discrete spectrum that we were setting out to look for, where does that show up? It's that spectrum I showed you, that spectral density was continuous. No amount of adding more corrections into more functions of E, which are each smooth, are going to make that not continuous. So is 2D gravity broken somehow? And the answer I'd like to assure you is no. You can still complain, where's the discrete spectrum, etc. And I'm going to tell you it's all going to be okay. For the next few slides, I'm going to tell you how this is all going to work. Let me talk about discreetness first. How many minutes do I have left? I have 7 minutes left. Okay, going to be interesting. I just finished the introduction. So what does beyond mean? So recall that we had this problem, this toy model, just to orient what we really mean when we talk about random matrix models. No abstract stuff, something you can code. Some of you who's finished coding it up and got these graphs. No one? Okay. Just too shy. Okay. Go back to your code and put in another thing and say, keep track of whether, when I compute the eigenvalues of the matrix, track of whether it's the first, second, third, etc. And then rehistogram, keeping track, color code, or however you want to do it. So we go. So this is the same problem, the same data that we computed before. Now what we see is the following. We have peaks. This is all the first eigenvalues of all the matrices across the ensemble. Second, the third, the fourth, etc., etc. The sum of all this, if I don't care about the ordering, gives me just that simple wiggle shape. But this is important extra data. And in fact, one of the striking things about it, if you think about it, is that there is discrete structure, even though it's also continuous. Let me expand a little bit on that. So each of these is a probability peak, probability of the first, the second, the third. All that Pn of E, where little n is, which peak I'm at. And so I can think of this as a continuous function, but I can also think of it as a discrete sum. There's some manifest discreteness, as really should be there. The matrix model does remember that there's underlying discreteness. And in fact, we can get at it if we can compute with the right non-perturbative technique. So this is all extremely non-perturbative data. And this tells you what those wiggles mean. The wiggles really have meaning. They are what I just said, individual energy level statistics. So although I cannot isolate particular energy levels, I can still tell you things about the individual probabilities of them. We're still doing probabilities, but there's a lot more detail telling us about an underlying spectrum. So looking back as to where this all came from, we're beginning to see the discrete underlying structure which is associated with the quantum mechanical black hole, which is hugely exciting. This is certainly something which we were not able to do in any approach in quantum gravity in this community, at least until now, at finite temperature. One of the nice things that occurs, which I can't help but waste time telling you about, is also the fact that these, as I go more and more to higher and higher energies, or what would be coming away from zero temperature and allowing the going off to the semi-classical limit, these peaks get narrower and narrower, their variance gets narrower and narrower, and they also bunch together more and more closely. And if you like, this is also a model of the emergence of smoothness, which we then associate with smooth space-time. We're seeing this in the matrix model as well. That's something we've also always wanted to see in a model of quantum gravity. And so the question arises, can we do this for JT gravity? I just did this for a Gaussian model. Well, that's hard enough. And the answer is yes. And there's analytic techniques using some beautiful mathematics and mathematical physics, computing Fredholm determinants of various operators that live in the matrix model, allow you to extract these peaks. Here are the first 15 or so. There's actually a lot of wonderful physics you can do with these peaks that are intrinsically non-perturbative. Okay, let me carry on. The second thing I promised. Oh, not quite yet. Let me just say one more thing. Little note, which goes back to observations of AAAS and some of their co-authors in a previous paper, which is that there's some really nice features that are coming out. The fact that we have a random matrix model is very consistent with a number of things. Some earlier work by Maldacena, Schenker at Stanford that told us that black holes are intrinsically chaotic objects, a very scattering you can do near the horizon. Compute OTOCs that interpreted the right way will tell you, out of time order correlators that'll diagnose chaos. It tells you black holes are actually maximally chaotic systems. And the fact that we're finding, or AAAS found, that the spectra that we're seeing are random matrix character fits nicely with other things we know about quantum chaotic systems, going back to Vahigos, Diononi, and Schmitz, that we should expect random matrix type statistics for the spectra of quantum chaotic systems. And so these things are sort of lining up very, very nicely. But it doesn't get out of the way. It doesn't get us out of the question of why an ensemble, which puzzled our community for a long time. And I still think that a lot of us are entirely settled as to what it means. My interpretation is the following, but I should say, that 2 minutes. I should say that there are, there's alternative takes, including some really nice work earlier connecting to ETH by Julian Soller and others. I don't have time to talk about. interpretation is as follows. And so now enters Wigner, right? WWWD. What would Wigner do? Okay, so here's an alternative history. So there's some Hilbert space we're trying to find, right? It's finite dimensional. It exists. There's some Hamiltonian we're trying to find in our quantum gravity problem, which should characterize these low energy states of the black hole. It exists, but it's a hard problem, okay? And there should be some definite answer, but it's really hard. So what do we do? Well, Wigner would say, well, maybe I can just characterize it. Give me all the data you have about this Hamiltonian, and you go, well, I can compute the leading order piece of semi-classical physics. It should be that Schwarzschild dynamics. And so asymptotically, all those spectra should be approximately continuous and look like cinch root E. And Wigner goes, okay, I'll write down all the Hermitian matrix models, all the Hermitian matrices, have that and just do statistics on them. You would come up with a matrix model, and this is what he would find. And this is just another way of saying what I did non-perturbatively, but we did it backwards. We started perturbatively, Hooft, trying to do path integral, what have you. Wignerian way is just saying, I'm trying to characterize Hamiltonians statistically. And in fact, some of that intuition was already in AAAS and already in the previous paper with Kotler et al., where they were already developing this intuition. But I think it really comes out very strikingly, the non-perturbative techniques and the non-perturbative formulation. And for me, this is really what this all means, right? There was a moment there where our community was going, well, maybe fundamentally gravity is an ensemble in some way. I think that's a mistake. Wigner doesn't think nuclei don't exist. They only exist as an ensemble. It's just a tool for understanding coarse-grained information about the typical behavior. Oh, my last slide. Thank you for being so generous with the time. So our path integral formulation then, summing over geometries and topologies. Again, I should mention, we also Euclideanize in order to make sense of the saddles and so forth, and to give us access to some of this technology. It is some kind of coarse graining. We sort of always knew that, but it's become extremely sharp as to what this coarse graining is in this kind of physics, this kind of scenario. We have smooth space-time. Space-time should, we still think, maybe break down in some way and become not space-time anymore. It should emerge from some underlying discrete approach. And the path integral doesn't do that. It just takes smooth space-times and does things with it. So somehow it's already sort of coarse-grained before it starts using its basic tools. But it is a powerful tool nonetheless. And see many, many things going on in this workshop for how powerful, in some cases very surprising, that has been. In 2 dimensions, we've seen that the gravitational path integral is a particular kind of coarse graining. It's doing this Wignerian statistics on candidate spectra. And so one of the things people are thinking is that maybe that's a clue for how we at least do something similar in higher dimensions. If we should be doing statistics, using statistical coarse graining to understand higher dimensional gravity, and maybe there's some limit we'll see gravity emerge in the same way we've seen here. That's still ongoing, and there are examples of that where you sort of have some of it controlled, what have you. There's still a lot to be done. What more can we learn from the two-dimensional case? I don't have time, I think, to tell you about some things I've been thinking about recently. But here are some slides. Other matrix models exist which are useful for studying spectra with gaps, which are very important for understanding aspects of the thermodynamics. I will jump to the end. Some really cool things come out when you apply this to other problems in black hole thermodynamics. Thank you very much for listening.
Jump from this, if you get a connection, the metric into the gravity versus the random models, but even within the culture, ensemble, there are different metric classes of these metrics that you can choose. So is there one-to-one connection between the metric you would write and the typical one ensemble? First question. Second one, sort of related is that what exactly new you could say from using this technique towards gravity? Things that you show for semicircle, all the stakes and edges are known facts where
Yes.
what exactly is the ingredient.
That's great. So there's several new ingredients. Let me answer the first part first. So now in the picture I gave at the end, at first you started just going, I'm going to write down a thing that gives me Feynman diagrams that I can treat as tessellations, and maybe that'll match my path integral. The second way of thinking about it, or more the Wignerian way, is that I'm looking at an ensemble of matrices in a certain class. But these matrices are now actually the Hamiltonians of the reduced gravity system. So there's a second Hooft who lives in this picture that I didn't have time to talk about. I took some slides out, which is that which is to do with something called holography, which is that we always expect gravitational theory to be equivalent to a non-gravitational theory in one dimension fewer. So what we're doing is we're finding a Hamiltonian of that non-gravitational system. And this is an ensemble of those Hamiltonians. So we can back out what the symmetries of that Hamiltonian must be depending upon what the gravity problem is. So indeed, there are many other kinds of matrix ensembles, and starting with some work by Stanford and Witten, they were able to realize that these correspond to different kinds of JT gravity despite beyond the vanilla one I wrote down here. I just didn't have time to tell you. In fact, the kinds that are best under control for various reasons that I didn't have to tell you are in these days are in the Outland-Zernbauer class, which it looks like you're very familiar with. Those play a very important role in supersymmetric cases, for example. No, and then you had a second part to your question that I've forgotten. Oh, what's new? Oh, right. Well, discrete microstates, we can actually begin to touch them. We never were able to do that before. It's very mysterious when you do the gravitational path integral. It's very mysterious why that knows about an entropy at all. Because again, where are the microstates, what have you? So we can say things about, oh, yes, it would be nice if we could find these microstates, what have you. And in some very special cases, beautiful work in string theory told us that we can count things and then do a flow. These things are protected and tell us about microstates that match the path integral calculation in the usual way. But we've never been able to touch those things and really work with them. Now we see we can get them access to them explicitly. We have statistics of them. Those statistics are chaotic, which also that's new in the sense that they're telling us about the chaotic behavior of the black hole spectrum. That's a new connection. We're able to make sense of that and learn things about the black hole in that language. We'd still like to have one definite Hamiltonian for a given black hole. That's still very hard. But in this Wignerian sense, in the spirit of what Wigner did for nuclear physics, we can do a lot with just the statistics. So I hope that's an answer. What does this bring to random matrix theory? A lot of my work, for example, showing that there are analogs of all of these things like the Tracy-Witten peak and all of that stuff. They're analogs of that in these gravity problems. Those are interesting problems from a mathematical perspective as well. I can write chapter and verse about all of the interesting things that could be done with purely random matrix model question as well. So there's a lot more to say, but these are some of the things. I think over there, yeah.
Thanks for the talks also there.
A little louder, I'm sorry.
I have two questions. So one, my understanding is that you said that there is a correspondence between the quantum theory of gravity and random matrix theory with certain potential D of M in terms of matching density of states, for example. Is there also a reverse process where you can write random matrix theory and ask what does it mean on the other side?
Yes.
So, and if so, what was that?
I mean, that's where we started, actually, right? You go back to the late 80s, early 90s, and double scaling random matrix models were understood, again, with this Hooftian perspective as telling you about some model of two-dimensional surfaces that should correspond to, say, some informal sector coupled to some gravitating sector in some way, maybe define some string theory. And it took a long time to sort out on the gravity side, gravity coupled to X, what is X? Do the hard computation and compare numbers. It's extremely hard. So it's easy to write down matrix models and double scale them. It's hard to know exactly what they're good for. In fact, for a long time, I think people were not even thinking we would come close to studying two-dimensional gravity models that had anything to do with this kind of model. So one of the other great things that came from some of the work a few years ago, AAAS and others, was the realization that these matrix models that we thought were useful for doing things in some corner of string theory are actually really useful for studying, if you like, much more practical, much more intuitive degrees of gravity, where you have gravity coupled to some scalar with some couplings that you can diagnose. So now there's a whole technology for working with much more general potentials for those scalars than the sort I described here, again coupled to gravity. And if you can give me a calculation, a leading order for what the density of states is, I can, within a few minutes, give you the matrix model. So there's some very powerful techniques that I and others have developed now quickly translating between these two things.
I'm sorry, let's look at the second question related statement that black holes are the fastest travelers. So, well, the question is, what does it actually mean? And, well, sort of seems counterintuitive to me, because if it relies on the density of states, I can always construct density of states by hand, just construct a matrix that does that better than whatever you have. So, like, what is the status? Is it the theorem that there's the mathematical theorem? Is it the statement about the inability to construct physical systems that do better than that? So, can you comment on the status?
To do better, my understanding is that fastest scrambler statement is an analog. It's not an analog. It's another way of presenting the statement that I said more recently, that they're in some sense maximally chaotic. And I think they were really able to prove a bound at that at least the chaos that's diagnosed by the Lyapunov exponent that you get from scattering, looking at the late time behavior of correlators, is maximized. So I guess I don't, off the top of my head, understand what it would mean then to try and build something that does better than that. You'd need to give me more than that.
So if it relies on the density of states, density of states is sort of depends on your essentially diagonal metric. I can construct any metrics I want.
The statement is, okay, I see what you're saying. The statement is not, that statement about the maximizing chaos is not about the density of states. It's about the OTOX. So it may be that you can find a loophole in the fact that there's some random matrix spectra statement about chaos as well. But I think the maximization, the saturation of the bound is in the context of OTOX. And I don't know if I can draw a connective line between those two things. Steve may know. I'm sorry, Steve. I put you on the spot.
You have to put certain straits on the kind of physical Hamiltonians that will satisfy this bound. You just pick a Hamiltonian, it's a random matrix. It will normalize, it'll randomize like in one time step. Okay. So you have to argue about a system where in a short time, order one time, things don't change very. Technically, you have n degrees of freedom, and you have to argue that in a time of order one, things only change by an amount of order 1 over n. A system like that, the typical thing you expect is 1 over n times an exponentially growing. The size of that exponentially growing piece. You have to imagine a system, a large number of degrees of freedom that doesn't instantly. There's a sparsity in the Hamiltonian matrix. That's
time for one more, or we're done? We're done. Okay.
The urgent questions. We can have more discussion over the wine and cheese. So let's thank you.
Thanks, everyone.